Drop a heavy load onto the center of gravity of an unsymmetrical steel beam, and something counterintuitive happens. The structure violently twists as it deforms. This diagram illustrates the reaction. Loading an unsymmetrical cross-section at its centroid induces intrinsic torsion, rotating it out of alignment. Our objective is this state on the right, pure bending. We need the point where a load causes straight downward flexion with zero rotation. For perfectly symmetrical shapes, like the standard I-beam in Figure 13.2, the ideal loading point, the shear center, matches its center of gravity. But remove an axis of symmetry to create a C-channel in Figure 13.1, and the shear center migrates completely outside the physical material. Designing a stable structure with these shapes requires us to hunt down and mathematically locate this invisible coordinate. To map exactly where this hidden point lives, we first have to look inside the steel itself and track how the material reacts to a downward vertical shear load. This diagram illustrates the internal stresses as shear flow. These red arrows show the stress traveling continuously through the top flange, down the vertical web, and out through the bottom flange. Notice how the top and bottom arrows point in completely opposite directions. The shear flow in these flanges acts as opposing horizontal force vectors, labeled F and F', separated by the total height of the web. In physics, an opposing push and pull like this is called an internal force couple. Because the top pushes left while the bottom pulls right, they generate a twisting moment, or torque, across the cross-section. Applying a perfectly vertical external load directly on the centroid intrinsically creates a rotational internal torque that tears the beam apart. This force equivalence diagram reveals the mechanical countermeasure. To neutralize that internal twisting, we must physically offset the external downward load, V, to the left by a specific distance, E. This creates an opposing external torque. The math to balance the system relies on a strict equilibrium equation. The internal torque, which is the flange force F multiplied by the web height H, must exactly equal the external torque, the vertical load V, multiplied by our eccentricity distance E. If we take that algebraic formula and divide out the vertical load V, we isolate our target variable on one side. The distance E equals F times H divided by V. By substituting the exact geometric area of the shear flow for the force F, structural engineers arrive at the final working formula. The distance E is defined by the flange width squared, the web height squared, and the thickness, all divided by the section's moment of inertia. Look at this sample calculation in example 13.1. When you input the real-world physical dimensions of the web and flanges, the complex algebra condenses down into a very exact answer. In this case, 46.35 millimeters. That single number is the precise millimeter distance from the beam's center where structural balance is achieved. When a heavy load lands precisely on that offset point in reality, the physics stabilize. The beam bends smoothly downward with absolutely zero twist. This exact mathematical principle is deployed continuously in massive structures. This hand-drawn sketch of an aircraft wing illustrates the concept in semi-Monaco construction, outlining the internal webs and flanges. Inside a wing, the internal ribs and spars function as complex, unsymmetrical channels. They have to perfectly absorb and manage extreme aerodynamic shear loads without violently twisting the wing out of the sky. Reliable structural design is as much about mastering geometry as it is about material strength. The precise location of an anchor point defines how the entire system responds to a load.